All right, so questions? Yes.
Could we more thoroughly cover Fermat's little theorem?
Sure. That'll warm up in a second. So I'm going to start writing. So the basic setup for Fermat's little theorem, we have a prime number, and we have a number that is not a multiple of our prime. Okay, because if it's a multiple, it's not very interesting. And it basically says if p is prime, and if a is not congruent to 0 mod p, then a to the p minus 1 is one more than a multiple of p. And it's just a fact that's always true if p is prime. So this is Fermat's little theorem. And so we can do some really quick calculations with this. For example, suppose we're working mod 13. So example mod 13. So p is equal to 13. I can take 17 to the 12th, and I know that's congruent to 1. Right, how do I know that? Because anything to the p minus 1 is one more than a multiple of p. So, bless you. So 17 to the 12th minus 1 divided by 13 is an integer.
Why is it 17 to the 12th minus 1?
P minus 1. So if we're working mod p, then if we raise something to the p minus 1, it'll be congruent to 1.
So p is 12?
P is 13, p minus 1 is 12.
And the formula is?
A to the p minus 1 is congruent to 1 mod p. So I'm setting a equal to 17. I'm setting p equal to 13. P minus 1 is 12. So this formula says 17 to the 12 is congruent to 1 mod 13. And the reason this is useful is because once we know something is congruent to 1, we can take powers of that and it's still going to be congruent to 1. Because 1 raised to anything is just 1. So if I want to find 17 to the 120th, that's 17 to the 12th raised to the 10th, which is going to be congruent to 1 to the 10th, which is just 1. So 17 raised to any multiple of p minus 1 is also congruent to 1. And so if we want to know what 17 to the 1000th is, we can find a multiple that's pretty close to 12. So let's see that. So it looks like 83 times 12. So 17 to the 996 is 17 to the 12th to the 83. And since 17 to the 12th is congruent to the 1, that's just 1 to the 83rd, which is 1. So to get 17 to the 1000th, I just have to bump up 4 more powers. So I can do something like this. So 17 to the 997 will be 1 times 17, and that's congruent to 4. 17 is 4 more than a multiple of 13. 17 to the 998 will be 4 times 17. which is going to be 3468, which is going to be 3 more than 65. So this is congruent to 3. 17 to the 991 will be 3 times 17, which is 51, which is going to be 12, because 13 times 4 is 52. So this is 12, and 17 to the 1000th will be 12 times 17, which is going to end up to be 9, if you trust me. Right, so that's a multiple of 13. So we just figured out on 1.5 sheets of paper what 17 to the 1000th is mod 13. So if we take 17 to the 1000th and subtract 9, we get this big, long, ridiculous number. And if we divide by 13, we get an integer. How big is that number? That's not too big. There you go. So it's a few digits. So it's a way we can find a power that's congruent to 1, then we can just bump up by multiples, and so we can make problems like this tractable. This program I keep using over here, I don't know if I've mentioned this or not. This is called BC. So BC is an arbitrary precision calculator language, but I just keep using BC space -L, and it does floating point, but you know, you can do 2 to the 19,937 minus 1, and it'll just show you the answer. So it's not limited by digits. That's a prime number. All right, other questions? I posted a homework set which I'd like you to write up and turn in on Monday, so you have a few days to look at it and then ask questions about it on Friday. But it's 2 sets of questions. The first is using Euclid's algorithm, which we're going to practice today, to find greatest common divisors, and the second is using Fermat's little theorem to I think do exactly the thing we're going to do today. No, that's the homework we're doing today. Different homework. So here's the homework I posted. Okay, this is better. So this is just working with finding what things are congruent to modulo 11, right? So just show some calculations, seeing what these things are which of these are congruent to 3 mod 7. Question 3, just kind of think about it. I'm not going to grade that one, okay? It's kind of open-ended. Think about it, see what you come up with. Question 4 is using Euclid's algorithm to find some GCDs. And then question 5 is a proof that the product of 4 consecutive integers is divisible by 6. I'm not going to grade that one either, but think about it, okay, and see what you can do, and we'll talk about it. But I'll grade either 1, 2, or 4. So, but write them all up, because I won't tell you which one I'm going to grade. And turn those in on Monday, so you can ask about them on Friday. All right, other questions? So what were the subjects of the latest lecture videos you watched? Well, parity, okay. What were the latest lectures?
GCDs and Fermat's little theorem.
Okay, and then applications?
And then applications.
Okay, so GCD, Fermat's little theorem and applications. All right, so application was parity. What about GCD? How do we find GCDs? Remember the name of the algorithm? Euclid's. So we're going to practice that today, but it's basically a little iterative algorithm on two numbers. Gets you the greatest common factor. Fermat's little theorem we just talked about. Other applications?
IFPN.
Yeah. UPC. Those are the main. I mentioned something about hashes, but we'll talk about that more in CSE 222. And crypto we're going to talk about on Friday. We'll talk about all kinds of cryptography. And Fermat's little theorem we just talked about a little bit. So, so let's take a look at some homework. We left off with this infinite number of primes thing, right? Not everybody got to that, so let's talk about this a little bit. So how many people worked through this proof and are convinced that there's an infinite number of primes? Like ready to talk to strangers and tell them this is true? So it's a proof by contradiction, right? We suppose if there's not an infinite number of primes, we can take all the primes, we can throw them in this bucket called P. Okay, it's a set. Every prime number is in this collection, right? So now we multiply all those numbers together, which gives us a big number B, and we add 1 to it. And we know that B cannot be prime because it's not in this collection of things. It's bigger than everything in here because we multiplied everything in here by other things. So B is too big to belong to this collection of primes. Since all the primes are in this collection, B cannot be prime, right? And if we add 1 to B, which makes it an even bigger number, it can't be in this collection of primes. So T cannot be prime, which means it's divisible by a prime. Well, all the primes are in this bucket, so at least one of these primes must divide T. But if you look at the way T is constructed, it's the product of all these primes. If you divide by any prime, you're going to have a remainder of 1. And so it's not divisible by any prime, and that's a contradiction. Because if it's not divisible by any prime, it must be prime itself. But we already said it can't be in that bucket because it's bigger than everything there. So the contradiction was our original assumption that this set P was a finite set. And if we take away that requirement that P is a finite set, then we can't form this number B, which is a product, because B would be infinite. Right? So we can't multiply an infinite number of things and actually get a number. So that's where the proof falls apart. And the Greeks figured that out. Greeks figured out lots of stuff. All right. Yeah, this looks a lot like what I thought. All right. So, do you want me to do the first one of these, or do you want to just jump into it on the board? You would?
I'd rather just get through it.
Yeah, I'd rather everyone just get to it, because you saw me do this on the homework, right, on the videos. So find a board and start doing these, and I'll walk around and see how you're doing.
Second pair is 1066, 572. I guess we can also put this in there.
would be
equal
100.
to something times
And then
15
equal that
plus
to something
Oh, yeah.
times 15 plus the remaining.
Say 100 equals
Something. Times that second number, which is
100
15.
equals to. Yeah.
Plus the remainder of whatever 16
We're
times.
gonna take
remainder, so divided by 15.
15. And then plus something. So 15 can go into
Why
plus
isn't it
100.
5 or 6?
8. No,
And
7.
then
7 times 15 is 90.
Three times, 2 times 15 is 30. So 4 would be 60. 6 would be 90.
Oh, okay.
So it'd be 6 with a
yeah.
remainder of 10, so we put 10 here.
Yeah, and then 6 in that blank spot. So we put 6 times 15 plus 10 remaining.
One more.
And then we do,
And then we'll bring down the 15, put that to equals. So 15, and then we'll be something times the remainder, which is 10 something. So that remainder, which is 10. Plus, whatever that actually is.
5.
Yeah, it is. Yeah.
This comes down here.
So 1,066.
5 plus 0.
Yeah, derivative made the two. And the greatest common factor is the,
So it's gonna be.
so it's gonna be 5.
No, it was only.
Next one is 1260.
So the remainder.
You know, once you get to 0, you basically get the previous number.
Alright, everybody got the first one, good.
Yes.
And we need a calculator for this.
Grab mine.
It's okay, I got one. Can I put 2 here and then subtract?
No. You could, but.
So, what you do is 100,
Speed times 1.
15, 100 equals 10. Bring the remainder and 5 over your remainder. Is yours?
494. I just did 1,066 minus 572.
Oh, yeah. Like an idiot.
No, it'd be 572.
Okay.
1,260. 1.
Be 1 with the remainder of 78.
So it goes into like 29 times equal. So 45 over
78 times 6, which gives us a remainder.
Looks like
No,
4 or 5.
it's 20. The remainder of 30. 78 times 6.
And what's the, like 4 or something here? 4 or 5?
It's 6. 6 times 78 is 468. Which gives us I was doing 498. 490.
Okay, so what's the first one? 7 times
468. The remainder of 46.
This is
Yeah, actually I have to put 8 in the calculator.
6. this
No, we're just, we want to
is
do this, rule, because 11's prime.
26 plus, and that's going to be 468.
Oh, so this is.
Three equals the remaining zero. And then
So
this
he
way across the board, greater zero equals six, yeah. There's
Divide.
No, there's one. Where you did it. Yeah.
27.
1260 and 45, yeah.
18 is the remainder.
18 battery at 6.
27. Yeah.
No.
There's that
This time it goes into 6.
So, and the remainder is mod and the remainder.
So it's 494 divided by 78.
No, I guess that would be
The remainder of 26. So 78 times 6 equals like 468. So it would be 494 minus 468.
the exponential and then
Yeah, quotient is 6 with a remainder of 26.
Oh, okay, that's where I got that.
sorry, if a with p minus 1 is congruent to 1 then
It's 27.
The greatest common name
what is
is
congruent to 1?
oh, it's you're on 45.
18 plus 1.
That's did you notice that I wanted
18.
Yeah, so that's just
all 6
5.
and 45 greater common denominator is 45. So 60 times 45 is
2.
the next one.
Okay,
So the
so no, is that what that is?
10.
yeah.
And the
And then the
I
next
was
one
doing the 46.
There's
27. 18 is
Yeah.
Wait, it doesn't. This number goes there.
We know that 7 is to the 10. But it's not. They're congruent to 1. You can't do that because that doesn't go
As if you take 7 to 10 and then square that.
Cool.
Well,
Check the one just to the right of that.
This one?
Yeah. The first equation that you wrote, is that really true?
Because the exponent is but I mean, we can do it right.
28, not 27.
Yeah.
Oh, wait, and it's 0, no remainder.
Right.
Confirming,
So 0 is.
confirming what we know. Yeah.
Yeah.
So what does that tell you?
So that's how
This
we
is
do
going
that.
to be 45 is equal to something times 0.
So we, which is congruent to
Plus, and then the remainder would be 45.
Well, that itself is already
That's 10.
Oh, yeah.
Yeah, you can stop right
Oh,
there.
yeah.
So what's the greatest common divisor?
45.
Yeah, 45. So if the first one ends with a 0, then one of your number divides the other. So that's your GCD right there. Cool, and the others look perfect too.
okay, you are set at 200.
No, I like it.
The last one is 1001 and 80.
Oh, yeah, it should be.
11 is
So I think
Yeah.
Oh.
Well, and if you want.
and remainder 77.
yeah, and then 1, 4, 7, and 11.
Yeah, and last one's 101.
Right?
Yeah.
So
seventh degree of something.
All right, so the 227.
So now we're going to have to do
Line of eight, not
Breakdown,
multiple.
yeah.
Okay, use for months to look here and calculate the following.
Oh, this is almost another formula. That's actually
Hey,
really
you
good.
said you wanted to work on this, right? Like, rewriting it.
If you're going to say that, why would you say 10 times 250?
We are, but what times are we writing in terms of 7? And then what's for?
I don't know what it just made. If I'm not all here, it was like,
Yeah.
the P
Separate out that.
minus congruent to,
That's multiple?
yeah, just
What?
Sure.
oh, I think it's like,
we know that
somebody
yeah,
did P minus 1 is congruent to.
I don't even know.
That would be.
Yeah, just that's how like
A to the P minus 1. That's usually side.
Yes. I always get confused, but yeah. When you raise the what number is that? So that would be no exponential. This where it's not
Oh, okay.
Because I'm saying P is equal to 1.
P minus 1 is 10.
P minus 1 is 10, so 7 is 10. Not 11 is 1 over 20. Yeah, that doesn't seem right. I don't think I'm doing something.
Well, that's the first one. That makes sense. And that was 7 to 20. 200. So, yeah.
So I'm not sure I agree with the last sentence here. 7 to the 11th congruent to 1. What the theorem says is 7 to the 10th is congruent to 1 mod 11.
Let's get these all located.
Yeah, so that's guaranteed by the theorem. So what about 7 to the 20th?
Yeah, because 20th is 7 to the 10 squared, which is congruent to 1 squared.
Yeah,
Some validation.
Okay. It's just saying that all of these. Yes.
Because he did this in the example in the video.
Yeah, I remember.
Yeah. 7 is now multiple.
7 to the 200.
Oh, yeah. Okay, we'll actually use that in 23.
7 to the
So the purpose of this is to try and find this
All right,
number.
so this
What else are they there? Yeah, too big to deal with. Is it, is it the homework that you have?
No, it's whatever.
So,
Looking at the, yes.
so then one
Oh, cool. Okay.
yeah, so
Even in odd.
So this is the theorem right here.
yeah. I'm just trying to wrap my head
I'm good at the left. That's yours. Perfect. Yep.
49, right?
Yep. But then you reduce that model 11, you get 5. Make sense?
All right.
All right, so you bring up homework 23. Go ahead and work on those. And that's basically find a product with a UPC on it, and check digits, and then do an ISBN. No, always give something between 0 and a modulus minus 1. So between 0 and 10 in this case.
This is equal to.
But that would get you most of the points.
7 to the 20th.
It's right here.
Actually, I was 22.
And we know this is congruent to 1. This is congruent to 1.
Yeah, it's
I never did this. Oh wait, then this would be 49. So this is 1 times 1 but times 49. So we know this is congruent to 49. Is that right?
Yeah. One detail that doesn't change your answer, but up here you wrote 7 to the 200th was congruent to 1 to the 10th, which is just 1, right?
Yeah, you said that this is 7 to the 10th.
Right. And this is 7 to the 20th to the 10th, right? So this, right, I think is what you meant instead of this. Right. 'Cause this is 7 to the 200 and 7 to the 200.
Oh, yeah.
Oh, okay.
So you use like your 720.
Yeah, this times this would actually be 7 to the 30th. Right?
Oh, yeah.
So if you do this, right, that's 7 to the 200. But if you do this to the 11th, that's 7 to the 30th. And then you multiply by 7 squared, and you get 7 to 226. But it's the same thing, because all this is just 1, right? That's the real 49. And the last thing is, what is 49 mod 11? Yeah, that would be your final answer. All right, cool.
And then
That makes
7 to
sense.
the 240.
So go ahead and look at homework 23.
Oh, it is.
Is that a real UPC? Okay.
So it's 0. We're gonna see.
Yeah, that'd be interesting to see. Okay.
Borrow your
Yeah.
7 to the
So you're 20 at 12.
So yeah, I might have to like equal that, but.
So go ahead and look at homework 23 if you want.
calculate the x1. So the US code. Do you have one of the notebooks? The notebook might have one of that.
The 5 we don't have, that's our
0, 26, 46, 0.
We have 7. What was it?
46, 0 with the 4.
There you go.
46, 0.
46, 0.
Oh.
And then
Times 7 to the 2.
26, 46.
So in this case,
Take
well, yeah, in this case, it's
3x.
So this is a shortcut, a lot of explanations, but the first 220 of them in this case, and then the last two by hand.
So we add the odd.
Base
Alright, cool,
of
great.
So do we just take 3x
Alright,
and 1 to the next 2x?
We did all the They added all the odds together, so just starting with the 0 and then hurry up.
So we start with 0.
Yeah, so we write
And then
up
the result is
0,
not
6,
0. Oh, we
2,
calculated this one once. And if the result is not zero, subtract it. So
And you may not find an exact factor. You don't need to actually.
Yeah.
You just want to get close to it.
12 times 3 is 6.
Where's the 3x?
Well, you do, yeah.
There's a map again as well.
There's 3x plus 3x. So we just do that.
Plus x2.
36. So just equals 36.
we're only left to 9.
And then for the evens, we add up all of the evens.
And then.
Okay.
Model.
No, that makes sense. Yeah. So 2, it'll be the other, every other one.
Oh, every other.
Yeah, Should be, yeah. 2, 2, 9, 6, 1.
Okay. I don't know why it's like.
Yeah, I've been looking at the way easy. 13. And then we do add those in also be 36 times 20. And then we do if it's not equal to 0, subtract 10.
Or even you could.
So we do 10 minus 6.
Why would you guys use red? Okay, cool. So it's a real eraser.
You just have to find what also.
Right? It exists and it's not more than cool. It's like the ISBN. All right.
I'm sure you can do it.
2, 4, 0, 0. Multiply by that.
Alright, here's a
But they're all basically
Here, write
the same
down,
idea, combination.
9, 7,
Of the bits, you do some kind of
3, 1, 6,
and multiplying them by different
Check out the more.
1, 0.
interrelates you can flipping two digits.
So is this x1?
Digits are different.
Yeah.
Yeah.
Is there a procedure to
Why don't we just do 3x1 plus x2 plus 3x3 plus
How much
x4?
error will they
This is just like a simpler
Well, Joel did in the video.
two bits.
You can just have it.
3x1.
Yeah, we can try this right here.
The first line is this.
3, 0.
That's it for that. Yeah.
Yeah, it shouldn't be random, check things too.
Here's another one if you want one. We have
7. So find something with a UPC in the back.
we not count the
We disregard that more.
Only up to
Do an ISBN.
Yeah. ISBN?
Okay.
Okay.
So, 5 and 6, it's not 0.
Trying to find one?
I think that's a doesn't make sense.
Unless that's not a.
It says if they're right here, it says if the result is not 0, subtract it from
And it should check out to be 1.
the final answer should result. The final result is the check digit. Which is 4. Negative 46.
There's a 13-digit version in there.
Or
so
maybe it
whatever
has to be a
this is.
10-digit.
Here's 2, 2, 4, 6.
From one to another. us
find
throw all
check
the
out.
in.
Yeah.
So you can see
Smooth part
this.
forward.
When you have 56 from doing the like 3x plus.
Okay, we're reducing mod 11.
So,
So what's 56 mod 11?
Now it's like an eye.
That's okay.
What's this called?
56 mod 11 is going to be 1, isn't it?
Yeah.
So 1 times 5 is 55.
5. So that is the check digit. 1, 2.
Is that not the check digit?
And that's not our check digit.
Okay, let's see what happens. And this is ISBN or UPC?
What is that wrong?
I think that's UPC. Yeah.
Okay, that might be why.
So,
That's what
They want the answer says
Well, you get to find more than this area.
Yeah, right.
108.
Well, it's all positive.
Yeah.
There's no.
Formula?
I don't think I have any books. That's sad.
Is it, do we always do model? Or is it just,
Oh,
mod 10.
which?
That would just be 6, which is still not 4. So,
Yes.
are we supposed to do mod 10 or mod 11?
For which one?
For 1, we're doing.
UPC is mod 10.
Yeah, well, we still get 6, which still doesn't.
So at the end, if the result is not 0, subtract it from 10.
Maybe you do.
Oh, so mod 56. Okay, so that would be negative 46.
Well, 56 is 6 mod 10, right? So you're always reducing mod 10.
6. Okay.
Okay.
So then 10 minus 6. So that was 4.
There's your check digit.
Alright, so let's try
Perfect. All right.
This is awesome. It's more likely to be valid than for
Yeah.
Oh, so this is exactly about that. Yeah.
So that's gonna be.
So it's sit there like remembering how to do
That's
That's the other ones I'm like. Well, actually, eventually then I did like do my function on my computer. Because I'm just like, I'm like time. Yeah.
Yeah, that's what.
Should be 9.
I wonder if I did
That's a lot more than 9.
These numbers are all multiplied by 3.
Look at my other guy.
9 digits all the way.
Are all just added together. No multiplication.
Yeah, there's a whole.
So there's an ISBN 10 you can use if you're having trouble finding one. That's one of my books. Note that I'm number 11,322,411th in the rankings.
Which one?
Yeah, I'll do it. The
Yeah, well, it's awesome.
Yeah, that number you. I think the one you just wrote was a 13.
I think I did it.
Zero.
I did this one.
And 10 minus 10 is 0.
Oh, no, it's
No, I'm saying it's this one because I think it's good. I counted 5.
Right?
So it would actually be 5.
In the first
They're gonna check it out like symbolize it's like a normal calculator to me, and he isn't really. Yeah.
Three times four.
Yeah. Plus, I also. That's why I try like not to use them when I'm over there. Work
I think so.
I mean, no, I mean,
Like I put it where it's 0 here and 10 minus 0
Usually
is
those over 5, 6, 7, 8,
10.
9, 10, 1, 6, 5, 9, 3, 3.
Oh yeah, that's why I
Is
like.
0?
Yeah,
So yeah, so
You know, like all my tests.
And the algorithm says that the answer is not 0, like oh, but if it's 0, this part is stupid. So yeah.
Yeah.
All right, so take another minute, finish playing up these codes, and then let's talk about some of this and some of the other applications related to this.
Oh, you got her checked.
That worked out.
Yeah, it worked out.
Cool. Someone's pen. Did you get the right digit?
Yeah.
Cool.
It's supposed to be the remainder. Anyway, that's the check is right.
Correct.
Okay, so I got it right.
All right.
That's so much to do.
So yeah, so check digits or check bits are things that we use when there's data that may or may not be compromised in some way, right? So you have a pricing code on a product, and typically if you're keying it in by hand before you had laser scanners, right? If you make an error typing it in, you might ring up a TV set as a candy bar, right? And it costs $1. But if you type in the whole thing, including the check digit, right? Well, if it was still a valid code, but typically if you swap a pair of digits or you type in a digit wrong, the check digit's not going to come out correct, right? You got a 90% chance that it's going to be the wrong check digit, and it'll say, you know, there's something wrong with this code. So it's sort of a first order protection against data errors. So parity, which I mentioned briefly in the video, is another example. So we typically use ASCII, and go back to the days before we had internet. When you wanted to talk to a computer, you usually did it over a phone line, right? So AOL, right? You pick up the phone, you dial the computer, and you used to connect it to something that was called an acoustic coupler, and it would actually send tones through the air, right? And there were these rubber cups that, well, I'll just get you a picture because they're cool to see if you haven't seen one. Right, so these kinds of things. I had one of these, I thought I was so cool. And the phone, right, so the old style handset with a thing up here you listen to and a thing down here that you talk into, and you'd shove it down onto those two rubber contraptions and it would make this sort of airtight seal, and one side would make tones that would go into the mouthpiece of the phone, and the other side of the phone, the speaker would make sounds, and there was a microphone in there that would pick it up. And there was no physical connection between your computing equipment, this thing, and the actual phone lines. And that was important, right? If you actually made a physical connection to the phone jack in the wall, the phone company would come and get you, right? So now you'd be liable for like messing with their equipment. But landmark ruling basically said as long as you're not actually connecting physically to the copper, you can send whatever you want over a phone, as long as it's not threatening, obscene, etc., right? And AT&T fought that for years. And they won that battle quite a few times, saying like, nope, you can't use this unless you buy it from us. And they didn't make fax machines or modems or things like that. So eventually a judge ruled, you know, you can make any sounds you want over a phone. So you started seeing acoustic modems like this and fax machines and answering machines and all this kind of stuff that AT&T really seemed to have no interest in getting into the business of. So this thing would just use sounds, but it was very error prone, right? If someone started yelling in the background, that's not a really, really good airtight seal, soundproof, and it would interfere with transmission. And so you get all kinds of data errors. And typically you just start seeing funny characters coming out on your screen. But here's an example. So this is binary for 65, which is an ASCII code for an A. Here's binary 67, which is an ASCII code for a C. And the only difference between these two is this one bit right here. So imagine I'm at home entering in grades. I've called up the computer at Clark with my acoustic coupler, and I get to you and I'm typing in your grade, which is an A, and it starts sending this pattern of bits, but at this point my dog sees a squirrel and barks, and that 0 changes into a 1. And your grade is now recorded as a C, right? So this happens, you know, fairly easily. So is there some way the computer knows that this was supposed to be an A instead of a C? No. So what could you do? You could send every character twice. I could send this character and follow it by the exact same character a second time, and then when this bit got flipped to a 1 and I resent it and the bit did not get flipped, it would say, hey, that's not the same character, something went wrong. And it would ask me to resend that last character. Okay, but that's problematic because when I want to send 8 bits of information, I have to send 16 bits. And this was a time when 30 characters a second was pretty standard, right? So very, very slow transmission rates. Don't want to cut that down too far. So the idea of a parity bit is here's the number you want to send, and if we use even parity, right, then we add one more bit, just 1, and we make it a 1 or a 0 so that the total number of bits is even in this case, so we would set that to a 0. And if on the receiving side it receives this, it counts the number of 1s, there's an odd number, it's supposed to be even, it says there's a data error. So it will catch single bit transpositions, and if the parity bit itself is compromised, it's still going to notice there's an odd number of 1s, it'll say there's an error. So any of these 9 bits, if they get flipped, it'll detect, but the obvious problem is right, if 2 bits get flipped, it doesn't know. It says, well, you got an even number of 1s, looks good to me. Now the chance of 2 bits getting flipped versus 1 is pretty small if we're talking about just some kind of random event. If someone picks up the other phone and starts talking or dialing, you're going to get a lot of transmission errors, and some of them may be detected, some may not, but you're going to know there's something going on. But this detects a single error, it does not detect 2 errors, and it cannot correct the error. It can say something went wrong, but it has no way of knowing what went wrong. It doesn't know which of these 9 bits is incorrect. It just knows one of them is, or maybe 3 of them. So there's other things we can do. For example, ECC. So I haven't bought memory in a long time. It used to be you could buy really cheap memory, or you could buy more expensive memory that said it had ECC. Okay, so this is an error checking and correcting code. And basically for every 32 bits of data in your memory, there were, I believe, 3 extra bits associated with it. And it was like a fancy parity check. It would tell you basically if any bits had flipped, and it could correct at least 1, possibly 2 of these flips. So that if you had an error in your memory, it could fix it up for you on the fly. And there was a time in the 90s when they were predicting that memory errors were going to be the norm, not the exception, because the densities were getting so high. And they hadn't figured out the shielding and such, and so there was just a lot of memory errors kicking in. So everything started doing these error correcting codes. So we use these all the time. Yeah, go ahead.
I've actually seen that. They usually sell ECC memory for like servers and
Okay.
like high-end machines. It's usually really expensive.
Yeah, it's definitely more spendy. And so the really cheap memory, it's like, wow, this is really cheap, I'm going to buy this. Didn't have ECC. The other great trick on Amazon is when they swap bits for bytes. It's like, wow, this is a 1 terabyte flash drive. It's actually a terabit. So it's like 128 meg or gig, and it's like tiny. And marketing is where the money's at. So we use this kind of thing all the time, right? So we have things like Md5. If you download a piece of software from the web, from a reputable site, usually there's something associated with it called an Md5 code. And it's a big, long code. It's not just a few bits. But it's a pattern of bits generated from all of the bits in this file. And if you look at the bits in that file and you try to recreate the Md5 code, you should get this exact code. And the idea is it's really hard to change that file in a way that still creates the same Md5 code. So everybody wants to download PuTTY. You're a vicious hacker, so you take PuTTY, the executable, and you start making changes to it to try to add things into the code to capture people's password and send them to you. Okay, you got to make a lot of changes in the code. If all you have is a parity check on the contents of that file, you figure out your parity, and if it's wrong, you just change 1 0 to a 1 somewhere in the file, and it looks like it's the same file, right? With an Md5 code, it's really, really hard to do that, because it's not just based on the bits, it's based on the bits and what position they're in the file, and so on and so forth. So it's a sort of error check, first against downloading something that's been corrupted through transmission, because you don't want to load a damaged executable, but also protect against malicious changes to the file. And most people don't actually check these things out, but you can take the thing you download and run a local utility to generate the Md5 and compare it and validate that it's what it says it is. So there's a whole gamut of these error checking codes. All right, let's talk a little about hashing since we've got time. And like I say, we'll talk a lot about hashing in CSE 222 when we get into data structures in winter. It's one of the data structures we work with. But here's the basic setup. Suppose you're trying to store phone numbers into the memory of your computer, and you want to be able to store 100 phone numbers. Okay, so a pretty typical approach would be to make an array that holds 100 integers, and then in each location in this array, starting with numbers bracket 0, we could store the first phone number, the second, the third, and so on. And if you want to find if a phone number is in your database, you can just search each of the elements in this array and see if that entry matches your phone number. And we could have a parallel array of names that might list the name associated with each phone number. Well, 100's not a really big number, but think of what you're doing if you want to find a particular number, right? So 8675309 or whatever. You start going through this array and you compare each number to the number you're looking for. And if you find entry 17 matches, then you can look at name 17. That's the name of the person. But imagine that this was 100,000 or 100 million entries, right? That's a lot of work to do that searching. So we'll talk a lot in data structures about different ways to organize information. One thing we can do is we can sort these numbers. And if we have a sorted array, how many people have played the game high-low? Somebody guesses a number and you say it's high or it's low, and they try to figure out what number you're thinking of. We can basically do that to find numbers in a sorted array. Okay, we're going to do that next week in 224. And that's better, okay? That gets us much better performance. But we could do even better if we did the following. Suppose and we're only going to use 7-digit phone numbers for simplicity. Suppose I made an array of 99,990,999 entries. And whatever phone number you had, I stored it at that location in the array. So if your phone number is 5551212, right, I would store that at numbers 5551212. And I would store the name of that person in my names array at the same index. And suddenly I've got a really, really efficient way to find out who belongs to a phone number. I take the phone number, I just pull out that element from the names array, that's the person's name. And if I initialize this array to say all blanks or something, and I pull out the name and it's blank, I know that number doesn't exist. This is really efficient in time. It's what we're going to eventually call order 1, meaning it takes a fixed amount of time to pull out your number, no matter where it is in the array. And really no matter how many things we store in this array, right, as long as we limit it to 7 digits and our arrays are big enough to hold all those numbers. But what's the obvious downside to this approach? Huge memory suck, right? We need all of this memory space available. And if we're only trying to store 100 numbers, right, most of the space is wasted. So we'd like to get the best of both of those. We'd like to be able to take your number and directly pull whatever we're looking for, the name, out of this array, but without having this huge chunk of memory that we're allocating to store this data. So this is where a hash comes in. And a hash, we basically take some key that we're looking for, such as a phone number, and we feed it into what's called a hash function. And this hash function spits out an index into an array. And so our array might only be 100 entries. But we find some way to take the 7-digit number and turn it into something between 0 and 99. And this process of converting from this big key to this small index, that's called hashing. And I'll give you a really simple example of a hash. So let's suppose our phone number is 7 digits, D0 through D7. Or through D6. Well, this is kind of silly because this is never going to get larger than 63. But I could add up the digits of this phone number, and I could say that's going to be the index that I use in my array. and ignore the fact that my array's got extra space in it. So if I want to store the number 5551212, I'm going to store that at index 5 plus 5 is 15, 16, 17, 18, 19, 20, 21. I'm going to store that at index 21. In names is going to have the name of the person, and numbers 21 is going to be that actual number. Yeah.
What about phone number 555-2121?
So that's a problem, right? So this is not a very clever hash function, because 5552121 is also going to hash to 21. That's going to give us what's called a collision. But if we can avoid that somehow, if our numbers tend to hash to different indexes, this is going to still be really good performance. You take your number, you calculate your relatively simple hash function, you say, oh, if that number is in my data, it's going to be at index 37. And you check numbers 37, if that's your number, you found it, names 37 is the name. So we'd like a more clever hash function, something like D0 plus twice D1 plus 3 times D2, and so on. So that if you just change the position of 2 digits or something like that, you get a different hash. But there's a whole science to creating good hash functions. Okay, it's topical to where we are right now, though, because this is just usually more modular arithmetic, right? So it's kind of like the same things we're doing with these check digits. You come up with some way to take your data and turn it into an index. And this works even if we're not trying to store something like integers. We could store names in a hash table. And how could we do that? Well, we could take the ASCII code of each character and add those together and reduce it modulo, say 100, and use that to say where we're going to store a name. So now if 2 people have the same name with the same letters in them in a different position, they're going to hash to the same location. You've got a problem. But other than that, right, there's a good chance different names will hash to different locations within reason. Now if I have 101 names, I'm going to have collisions because I'm only hashing to 100 possible things, right? But the idea is usually your space of things you want to store is huge, but the actual set of things from that space is pretty small. Right? There's a lot of 10-digit combinations of letters, but there's relatively few 10-character combinations that are actual names of students. Right? So if we could hash to one of 50,000 different locations, there's a good chance we'd get unique hashes for each student. But if we tried to hash all possible 10-character names, right, that's 26 to the 10th. That's a huge number. And just to go on the computer science angle of this, what this means is that we can start to think of these as super arrays. Now, a normal array, if we have an array called X, how do we index this? We say X bracket 0, we say X bracket 5, we say X bracket 99. These indices are integers, starting from 0 going up to the size of the array minus 1. If we think of this hash function as being in the mix, we can start thinking of this as an array that we can index with strings. And the understanding is you take this and you run it through your hash function to get a number between 0 and 99, and then you pull off that element. But imagine an array that you can access with a name, or with a float, or with an executable file, or with any other object that you can think of. You could actually use that as an index to pick off an element from this array. That's a really freaky kind of thing. So this is something called an associative array. And we can implement this just by doing some simple number theory, usually just some modulo arithmetic. Combine things and reduce modulo however many spaces we have. Associative arrays are powerful. Okay, there's a lot of theory that says this is basically how our brains work. You say Izod and you pull up all kinds of things that are associated with that name. Office location, office hours, good questions to ask, things like that, right? That's kind of how our brain seems to work. We work by making these associations, and this is a way that we can actually create these associations in software. So this is a really, really powerful way. So when I first learned about this for the next like half a year, everything I did was an associative array. That was it. Didn't matter what I was asked to do. I found a way to do it with an associative array. It's like this really, really powerful hammer that like, you can beat anything with. So we'll play around with that in winter quarter. And we'll come back and see some of these modular operations that we use. And there's a lot of science, a lot of math to how to pick a good hash function. And there's a lot that goes into how big should this underlying array be. And it turns out if you make this a prime number, you generally get better performance. If you make an array whose length is 17, it works a whole lot better than if its length is 16. And we'll talk a little about that in 222, but that has to do with how we deal with collisions. Basically, if we have two things that hash to the same location, you can rehash, right? So we put a second variable into our hash function, which is the attempt number. And the first time we hash with attempt number 0. If we get a collision, then we hash with attempt 1. And if that collides with something, we'll hash with attempt 2, and so on. And that starts degrading your performance from being a single operation, but it's not too bad. All right, so that's another application area. All right, well, I got 5 minutes, so let me talk about crypto a little bit, and we'll get into details on Friday. What's the basic idea of cryptography? What does cryptography mean to anybody?
Basically, writing your information in a way only you really can understand.
Okay, writing information in a way that only you can understand, right? And what are some ways we can do this?
Morse code.
Morse code, right? If you're the only person who knows Morse code, you can write dots and dashes and code your message, and to other people it's just a bunch of dots and dashes. Binary, same thing, right? If you're not hanging around with computer science students, guarantee most people won't be able to read that. I think Da Vinci wrote things backwards. He figured out how to write reversed. Ciphers, what's a cipher?
Like the Caesarian cipher where you just shift the alphabet.
Yeah, so Caesar is credited with this idea of just add a certain offset to each letter. So if your offset is 2, A becomes C, B becomes D, C becomes E, and you write something and it just looks like gibberish because it doesn't look like words anymore. But if you know that this was created by adding 2 to each letter, you can subtract 2 from each letter and decipher it. If you know how Morse code converts letters to dots and dashes, you can look at the dots and dashes and decipher it back into the original. If you know what binary is, you can look at these 1s and 0s and decipher a message back into the ASCII characters. So there's a way to encrypt or cipher, right, your message, and there's a way to decrypt or decipher your message to get it back into the original. And people have been using ciphers for thousands of years, right? Why? Because we've rarely had secure communications available. If you wanted to send a message, you wrote it out, you handed it to someone, they got on their horse and they rode across the land to whoever the recipient was. And if somebody intercepts them on the way and steals their bag, they can read your message. So you find a way to make it so that even if somebody else sees this message, they don't know what it means. But historically, a problem with this has been, if I'm going to send you a secret message, and I'm going to code it in some way, you've got to know how it was coded so that you can decode it. If I'm adding 15 to each letter, you've got to know 15 is the key, and I have to subtract 15 from each letter. If I'm using, AES on my laptop to encrypt something, I've got to use a password. And if I'm sending you an encrypted message, you've got to know what that password is to decrypt the message. And there's a few problems with that. One problem is, how do I get the password to you? How do I send that to you securely? If we meet in person, I can hand it to you. But if we're not able to meet in person, how do I send you the password securely? It's the same problem as sending the message securely. So maybe I use a different code, or maybe I use a really, really trusted courier, but it's a fundamental problem. This is why when you make a connection through PuTTY the first time, it gives you that big long message saying this fingerprint can't be validated, right? You've got to have some way to start the process. The second problem is if you decide you don't want this person to read your messages anymore, you got to change your password. And the third problem is if you're sending messages to 10 different people, you got to have a different password for each one, or you've got to trust them all equally, so that if one of them turns out to be a spy, right, you can't use that password anymore. Well, now you got to get a new password to the other 9 people somehow, right? So huge sort of logistical problems with this approach. And that changed a few decades ago, thanks to math. Yay, number theory, with the invention of asymmetric ciphers, so public key ciphers. And that's where we're going to try to finish up on Friday, is looking at public key ciphers. Public key cipher, basically, you have a way to encrypt a message, you have a different key for decrypting, right? And everybody can be given the same key for coding a message, but only you know how to decode it. And knowing how to encode the message doesn't tell you how to decode it. So if the coding method is to add 13, the decoding is not to subtract 13. It's something totally different. And theoretically, it's something that you can't guess just from knowing that to encode you add 13. So that was the real breakthrough for public key ciphers. So we'll play with some of the stuff. We'll look at Caesar ciphers, shift ciphers, transposition ciphers, and then we'll start working on the public key stuff on Friday.